How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at multiple bonds practice problems. So, number one, which of the following statements is true for a typical double bond? Well, a double bond is stronger and shorter than a single bond. That is a true statement. A double bond consists of one sigma bond and one pi bond. That is also a true statement. A double bond imparts rigidity to a molecule. That is also a true statement, right? The pi bond makes it unable to spin around that internuclear axis. A double bond consists of two shared electron pairs. Yes, two pairs. So a total of 4 electrons. And then E, all of the above are correct. Yep, that's our answer right there. All those statements are true statements for a typical double bond. Which is true regarding a typical triple bond? Well, let's see. A triple bond consists of one sigma and 2 pi bonds. That seems to be a true statement. Triple bonds consist of 3 shared electrons. No, if they said 3 shared electron pairs, okay, but they didn't, right? Triple bond consists of 2 sigma bonds and 1 pi bond. No, right? It's 2 pi bonds and 1 sigma bond. Triple bonds consist of 6 shared electron pairs. No, so close. 6 electrons, but not electron pairs. Too bad for that one. Triple bonds are longer than single bonds. Nope. Right? If they switch those around, that would be true. So the answer is A. 3. Circle the correct options in parentheses. Electrons in sigma or pi bonds remain localized between 2 atoms, and electrons in whatever other option can become delocalized between more than 2 atoms. All right, well, let's see. The sigma bonds are the localized bonds, right? So if I have, let's say, a carbon bonded to a carbon, these sigma electrons are stuck in between those 2 carbons. Electrons in pi bonds can become delocalized between more than 2 atoms. So if we had a multiple bond, right, if we had these p lobes overlapping above and below, they can become delocalized and move on to in between these 2 carbons too, if the structure warrants it. How many sigma bonds and how many pi bonds are shown in the following molecule? It always helps to draw these out. So I got CH3, I got CH2, I got CH, I got CH, I got CH2, I got C, I got CH. And the reason that you draw these out is so you can go, hey, wait a minute, carbon I know likes to make 4 bonds. It's missing a bond here. It's missing a triple bond here. And then I think everything else looks good. So let's count how many sigma bonds. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 sigma bonds. And then count the pi bonds. I got 1 here, I got 1 here, and I got 1 there. So I have 16 sigma and 3 pi. 5. Which of the following molecules or ions will exhibit delocalized bonding while obeying the octet rule? So we're looking for structures that have resonance, but they also specify we have to obey the octet rule. So let me draw these out. If I draw SO2 out, it's going to look like this. And now, hey, wait a minute. Why did I put the double bond on this oxygen and not on this oxygen? That tells me that there's resonance. So we're going to have a second resonance structure. That's going to look like this, which tells me that these pi electrons in that multiple bond are actually delocalized. They're going to not just be between this oxygen and that sulfur. They're not going to be just between this oxygen and that sulfur. They're going to be kind of moving over the whole molecule. So SO2 looks good. SO3. Well, if I draw that out and I follow the octet rule, I get a structure that looks like this. And now you go, hey, wait a minute. Why did I put the multiple bond between sulfur and this oxygen? Great question. That tells me there's resonance, which means that these pi electrons aren't stuck in between just those 2 atoms. They're going to be moving around the whole molecule. We have delocalized electrons in SO3 as well. And if we do SO3 minus 2, well, the Lewis structure for that while obeying the octet rule is going to look like this. And now there's no resonance. So not that one. So there you go. Number 6, what is the hybridization on each of the carbon atoms in Okay, here's another one. Draw it out. I got C with 2 hydrogens, and then another C, and then another C with 2 hydrogens. Now what's going on here? Well, there must be a double bond here and a double bond there in order to make sure carbon is happy with the octet making 4 bonds. So what is the hybridization on each of these carbons? Well, for carbon number 1, there are 1, 2, 3 domains, so it's going to be sp2. For carbon number 2, there are 2 domains, so it's just going to be sp. And carbon number 3 looks just like carbon number 1, so it's going to be sp2. All right, I hope you found that helpful. See you in class. Goodbye.